I'm going to move to the next speaker, Lapo Naldoni. Lapo has a degree in building engineering and architecture from Alma Mater Studium, University of Bologna, Italy, where he is also a teacher assistant of architecture planning. He developed his thesis focusing on mud construction and robotic informed deposition on tension fabric. The work has been presented and published at ISM Symposium 2018 in Boston. Currently, he is a member of a WASP R&D team and works on 3D printing and at different scale with polymer and fluid dense material. He has worked as a computational designer at Mario Koselna Architect. I think today you will be presenting low-tech, high-tech from the raw earth to 3D printed architecture. There's a lot of earth printing today at this session, end of session. So I leave you the screen, Lapo.
Thank you. Thank you for the introduction and thank you for the invitation. And congratulations to all the speakers because a lot of super interesting stuff regarding 3D printing and super nice printed part. So thank you all. I try to share my screen. Okay, thank you. So today I want to show you some of the projects that we have done in WASP regarding the use of local material like soil in architecture. So just a short introduction of WASP. That is a company born in 2012 by an idea of Massimo Moretti. That is to answer to the basic needs of human by using advanced technology. And to do this, Massimo Moretti started taking a look to this small insect, and that is a pottery wasp. So this is the reason of our name. The acronym World Advanced Saving Project is for joking. He started understanding which is the best way to use local material as the wasp to create shelter. So obviously, from the beginning, the idea of using soil is the dream of WASP. But at the time, it's quite difficult to have the effort, to have the money to reach this goal. And for this reason, WASP decided to start by selling a small machine able to work with clay and polymers at a small scale. So the needs are not only houses, but we can divide these in 6 different fields. And for this, we developed a lot of projects and different machines. So as you can see here, we have food, work, house, art, energy, and health. And as you can see, we work at different scale with different materials for the technopolymer to recycled plastic, to clay, and to raw earth. As I was saying, Massimo had a vision, and from this vision, we create project. And when these projects are ready, we create product and we sell it. And in this circular movement, we enlarge our vision and we enlarge our possibility to push our research. So WASP is totally internally financed. But now, okay, I can start speaking about my research, the research that I made with my team. And I think that we can start from this question, no? So all the people that now we are in the afternoon. So from the morning to the afternoon, a lot of people spoke about printing in architecture. But yeah, we think that the answer to this question could be related to the material, because by using 3D printing and more in general automated construction, we can adapt our mix and our morphology to all over the world. So by changing the composition of the mix from the binder to the aggregates, we can have a local-based mix able to be more adaptable to the local condition and to the local possibilities in terms of material and in terms of economy. And with the low quantity of energy we can go to the mixing phase and to the printing phase and arrive at architecture. No, so if it's possible, because it's not possible in all the countries, and if you use soil and vegetable fiber, you can have an architecture, a sort of architecture biodegradable. No, so if you remove the roof or the coating protection by the rain and atmospherical agent in general, you can come back to local raw material. The second answer could be the design process, no? Because as all the people know, with printing, you can unband structure, installation, all the system and the shading. And I am agree when we say that unbanding function inside a sort of skin could be not the best option for the future now, because if you want to come back and making some variation on the architecture, it's quite important to have separated all these functions. But I mean, in our case, if we are using a material with a very low CO2 emission, like raw earth, I mean, it's not important to understanding the reduction of material, the reduction of time, the reduction of the duration in the time, because if we're producing a shelter without using a lot of energy, no? So it's more important to optimize to other aspects. And finally, the morphology, no? Because with 3D printing, you can change a lot of different morphology in your architecture. And finally, on the architectural side, we think that the most interesting thing is related to the short way that an architect can have from the design to the 3D printing phase now, because in traditional building site, you have the creation of blueprint and the interpretation of blueprint. So if you use 3D printing on site, you can reduce a lot this way, and having a direct control on the building site. And as architect, you can say that you are building house and not building blueprint. But how we do it in WASP? We start in 2015 with the Big Delta, that is at the time the biggest machine in the world for 3D printing. But this machine had a lot of problem because it's not really usable in this field. There are some problem on the providing of material, on the speed of the machine, on the control of the machine, the precision. So we decided to jump to a new technology that is named Crane WASP, and is inspired to the normal crane that we have in all the building sites. And we work to optimize the speed, the weight, and the time to assemble this machine. No, so all is designed to be assembled by 2 men. So the manpower needed is not a lot, and you can reassemble this machine in 1 day. So I mean, all the weight are designed to be moved by a person. So we work a lot on this because we think that it's very important to have a machine able to be adapted at all the different sites. Because if you want to print on site, we need to be adapted on the site. For this reason, we know that the dimension of 1 crane is not enough to complete an entire building. So we developed this machine able to be adapted and used not only in base configuration, so with 1 crane, but in a collaborative way. So with a sort of intersection area that all the 2 printers can print together, or in parallel, in simultaneous way, so in parallel. So we have no collision, and we can print a different part of the building at the same time. So all the beam structure that we use to move all the electricity providing and the material providing and the water provided is constructed with aluminum beams, and is a modular system. So we can redesign in each case our system. I mean, as I said, we are speaking about automated construction now. So we have worked a lot in these years on the providing of material now, because it's very nice to say, okay, we use local earth, but it's quite important to understand which is the way to, just some simple example, remove stone from the soil, or have a material with a right dimension of aggregate now. So the curve of the aggregate have to be nice. So we create a system divided into container, one for the material providing, with all the disc screen separator, the excavator, and all the system to convey the material from the earth to the mixing system. And in the second container, the real 3D printer, so the printer and the continuous feeding system that is our pump. And now some of the project that we develop along the time. This is Gaia. That is the first project that we developed in 2018. Is located very close to me, 20 meters. And the goal of this project is to show to the people that it's possible to print house by using soil, because at the time there is no example, no real example, physical example. So we need to show that it's possible to create a room of 20 square meters with an high level of living quality now. So we use a timber structure to create the roof, because we want to stay inside all the regulation of the Italian code. And we use local material with the adding of straw, rice husk, and lime. It is the stabilizer that we use to reach the pumpability and the stability of the material. I mean, we work a lot too on the definition of the toolpath for the machine. So we start working on a small piece and understanding, we print some mockup, just understanding if it works, if we can optimize the internal design of the wall, just to avoid the shrinkage, because at the time we have, I mean, a shrinkage on the Z direction around 8% and around 1% on X and Y. So we work a lot on this to controlling the shrinkage and don't having a cracking, and to creating a wall with insulation inside and ventilation in the external part. So as you can see on the schematic view, we have a natural ventilation from the north side to the basement, and from the basement to the external part of the wall. So to reduce the temperature in summer and remove moisture in winter. I mean, from the simulation, we're thinking to reach a U value around 0.2, but realistically, when we made all the real test, we know that we have an insulation around 0.3. So to be honest, I want to say that this is not the right number. It is quite easier. Is less, sorry. Another project is, oh, I made a mistake on the name, is the staircase that we made with the IAC of Barcelona. We print these in January, and we print here in Massa Lombarda, so on site, but inside our facilities, so we can control more the quality of the printing because of this small piece, no? So we can control all these parameters, and with the nice design of the guys of the IAC, we create this structural system to insert the staircase inside the wall. Tecla is one of the last projects that we developed. It is based here in Massa Lombarda, and we finished to print in the 2020, but we opened this in 2021. We spend 200 hours to print these by using 2 cranes in a collaborative way. I mean, here there are some data about Tekla. As you can see, we use 80 tons of material. So we work a lot on the providing of local material because it's easy to make a mock-up with 1 ton of materials. But if you want to reach this number, you have to work a lot on the optimization on the screen disk separator, on all the system that you need to mix the material. From the left to the right, we have some of the mix design that we developed with Mapei, one of the biggest Italian company for chemical additive for architecture. And we use a binder that developed Mapei that is created for soil, and an extra part of lime if it's needed. So we made a lot of different tests. As you can see, the blue part is the water. So as you were saying some minutes ago, the usage of water when you have to pump something is really important. If you want to reduce and enlarge the strength of the material and reduce the shrinkage, you need to use more sand in our case. So we work a lot on this. This is only a part, the last part of all the experimentation that we made for Tekla. In the central part, there are some of the different sections of the wall. We're starting from a mock-up, that is the one that you see on the right. And the blue part is the structural part. So all the white part of the mock-up or the Tekla house is not structural. We decided to reduce the amount of material from the bottom to the top in order to reduce the weight of the wall and to have only the needed material for the structural resistance. Here's some image of the building site. As you can see, we divide in different sector all the toolpath of the machine. And with this, we can control the collaboration of the 2 machines in order to don't have collision between the 2 cranes and push the speed at the maximum. No? So we control the previous layer time, and with this, we push more than we can. Some image of the interior of Tekla and a schematic view of what the architecture studio Mario Cucinella architect developed to embed different function of this kind of skin, because when we spoke about Tekla, I think that we can speak about the skin of the building that is a multi-performance wall. I jump in another project, is Evolutional Farm, that is ongoing because we are working to close this project. We are working just to closing the roof and some aspect of finishing. It's a very big project because in plan is 200 square meter plus another small building very close, Dependance. We use 2 cranes and we print in parallel. But we use the crane in different positions. So we move 5 times the crane in the building site to cover all the area of the building. So we spend a lot of time to do this. And in this case, we use local materials. So we spend something like 6 months to develop a mixed design for these buildings. I know, because to be honest, I have to say that if we want to use local material, we need time to make tests, to make chemical tests and physical tests to know that if it's possible or not, because now is not a solution ready to go. We have to understanding a lot of things and set all the parameter of our system to be able to do this. One of the last projects that we will present is very close to you because it is in Wiesbaden and is for an American artist. For this project, as you can imagine, We don't use local material because we are in the middle of Wiesbaden, so it's quite difficult to excavate something very close to the building site. So we use a premixed material based on clay, lime, sand, and rice husk. We use a single crane because it's a very small project, it's 9 square meter. And yeah, the goal is to be very, very fast and very precise to create these super nice small art piece. Finally, the last project that I want to show you is the project that we developed for DIOR. And we will present this in October, so 1 month ago. It's located in Dubai on the beach in Jumeirah. And we print with 2 cranes and we spend 120 hours. Is a sort of evolution of Gaia, if you want, because it's circular, but is more larger than Gaia because we are speaking about for each pop-up store of 40 square meter. And one of the goals of the project is to realize the external surface with the pattern of the maison, that is the canage. And we test a lot these to reach the goal, because it's not easy to control a machine able to print it at architectural scale with the finishing that the maison want for the external part. So this is one of the main difficult that we have in this project to satisfy all the requests. So yeah, thank you for the attention.
Thank you. Many large projects. So I would like to ask, with 3D printing in larger scale, the funny thing is that a lot of the machinery is bigger than the architecture and the building itself ends up to be. So, and then you are dealing not only with that assembly throughout, like, I mean, if you are going really large, then you keep reassembling unless you assemble everything in advance or moving it around modularly as you print. And then you're dealing with material differentiation at the site, and then you're dealing with the site changes on the site itself in terms of night and the day and the sun and not sunny. What is the most complex part of this entire project? What is the most constrained area of the project when you guys are on the site?
Yeah. Good question. Yeah, probably one of the biggest problem that we have to fight when we are on site is the control of the climatic situation. No? So the temperature, day and night, winter and summer. So it's not very easy to do this because it's quite easy to have a mixed design based on local material. If you have the time, that is the first needs, and person with the right knowledge in terms of use of raw earth, you can have a printable mix. But this mix can totally change the properties if you don't control the condition in the building site, no? Because as all the people that print with concrete know, the layer time is the base, no? If you don't reach the right layer time, you destroy all the material that you have. You can have the best concrete in the world, but if you don't reach the right layer time, you don't reach the goal. So in our case, to control the external, the climate condition is, I mean, probably the biggest problem now. If you take a look to the history and if you take a look to the use of concrete in building site, I mean, it's possible to control this in an easy way, no? We need only time, because it depends from the quality that you want, no? If you want the perfect wall, probably printing indoor with all the condition controlled in small part is the best way to do architecture with 3D printing. But if you want to stay on site and reduce all the cost and the emission related to the transport, the installation, so we think that using a lightweight machine like the one that we use and in the future, probably material with a more elastic condition of usage probably could be an option, because I mean, I don't want to speak about the future of the construction is the one that I present. We are working to create an option. So I don't know, probably it could work or not. We think that if we don't realize the right number of study case to spoke about, it's quite difficult now, because otherwise we have a lot of theory, but nothing to touch and understanding if it could work or not. So now we started to work on it, and I know in the future we can say if it works.
Right. I mean, it's you have also, I mean, the challenge comes in two sides. One is you have a high exposure to the air as you print the entire surface. And then you also, I mean, if it starts just raining as you're printing, I don't know.
Yeah, but the rain is really not a problem, the rain. I mean, when we was in Dubai, we closed the building site with a tent, because we are in Dubai in August, so we print with 45 grid, so it's impossible to stay under the sun. But I mean, if you are in Europe, and you have to consider that we are using soil and not concrete, so we have layer time around 20 minutes, 40 minutes. So we have the time. And if we go faster, we can stay inside this layer time. So we can solve all the problem with the lamination of the material and failure of the material. So I mean, it's not concrete, is slower than the concrete, and the properties are very different. So it's possible to do this. And I mean, yeah, as you say, that the air and the sun probably are the biggest problem if you don't want to cover the building site.
May I, because I really, I mean, first of all, great presentation, and yeah, impressive projects, yeah, with the idea of local materials. What I was wondering is, so you provide basically the machines, and then probably technicians that go onto the site, yeah. But then you gather all this local knowledge about the materials, how to use it with your printers. So I was wondering, how much of this knowledge do you share? Do you share on your website? Because your business model is the machines, yeah, the renting and improving the machines. But then the materials, if they are local, I guess it's more about really sharing that knowledge, even across different countries. Yeah, if I'm from Italy, maybe I can even contribute from some of the knowledge from Dubai, or maybe someone using your machine in Kenya. So I guess it's a little bit also about building a community around your machineries and sharing the knowledge. So yeah, I was wondering if you, yeah.
Yeah, this is the way. Thank you. I mean, we are working since 2 years with the IAC of Barcelona, and now they have a machine, a crane like the one that we use. And it's very interesting to have this sort of community and working together and understanding the properties of the machine with different local material, no? So it's really important to have this feedback from local manpower and local knowledge in terms of use of the local material. I mean, in the future, probably we can imagine that WASP will have different machines around the world, and have the technician locally, but not only locally, because we can control from remote by using the web. So as in the case of Dubai, we made some modification on the controlling system on the crane from the Italy to Dubai in real time. So by using the remote control, it's very easy to do this and to share different information and enlarge this, no? And if you imagine to merge together all these database and find a way to use it, because merge the database is quite easy, but use the database in the right way is more difficult. But if we work on these and we find a way to do this, in the future, we can have a sort of platform where people can merge together all the different use of local material and of 3D printing related to the local material.
Thank you.
Also,
Oliver? Yeah, Oliver, you unmuted yourself. No, good.
Yeah. You also mentioned that you print at the same time with multiple of these printer. So is it that you guys have an interface for toolpath generation that automatically takes any kind of given design, and then it really segments it and distributes it between each of these machines in an automatically, or it's really done manually at this stage and it's something to be done?
It could be very nice.
Okay.
We developed internally a system based on Grasshopper, able to divide the entire toolpath. Because I mean, when we develop our project internally, we work directly on the definition of the toolpath, so polylines. And we develop a system able to directly control the two crane from Grasshopper, and understanding the position of the machine, the speed of the machine, reduce it just to avoiding all the possible issues of the printing phase. So is an automated solution for the controlling part because it's totally automated. But yeah, it's not automated the conversion from mesh to toolpath because we develop custom these on Grasshopper.
And what is the tolerance right now, like about your construction tolerance?
Yeah, good question. As I said, I think I said, yeah, in Gaia, we have a lot of shrinkage in Z. And this is mainly related to the large use of straw. In the Tekla project, we have a final shrinkage under the 1%. So when we put in Tekla the window and the door, there is a very low tolerance. Now you have to imagine that in the circular window, we have a tolerance of 3 centimeters. So it's very easy to close the gap when we fix the window.